Alright, in this activity we're going to take a step test like we've done before from 10 seconds to 70 seconds where we set our heater to 70%. From that we'll be able to obtain our data. It'll go up, but then it'll go down, something similar to what we've done before, but then we're going to fit a Laplace transform to that data. Or I should say we'll take a Laplace transform of the first order plus dead time equation. And from that Laplace transform, we'll be able to create an analytic solution for what all of the times should be, how the system will change as a function of the heater. And hopefully that will help you to be able to take this concept of Laplace transforms and actually apply it. That's something I've seen is pretty hard for people. So go ahead, first let's just run our code. What we're going to do is we're going to simulate this step test, and then we're going to fit it to this FOPDT model where we have our deviation variables. T prime is equal to T minus steady state temperature, and Q prime is equal to Q minus the steady state heater value, which would be 0. We also have, and that's what it's explained right here. Then we're going to generate impulse response.png and the impulse response CSV, so that if we have problems, we can always go back to them. Similar to before, we're going to clear all, close all. Then we are going to collect the data. We will try to read the CSV we've created, and if we can't, then we're going to go ahead and simulate. Pretty standard simulation code by now, hopefully. We'll start our timer, we'll take the time, we'll take the temperature, and then we'll pause for should be 1 minus right there. And then we'll pause the remainder of a second. Finally, we'll turn the heater off, and we'll write our CSV, and we'll export our PNG. If we're not able to, if there's some error there, we'll make sure that the lab turns off, and then we'll clear the lab variable. So we'll go to that point, and then we'll talk about how we derive the Laplace transform. Alright, let's do this analytical derivative together. If you're scared of Laplace transforms, that's okay, I am too. It's actually not that bad. The whole concept is we're converting to another time space, another sphere, another dimension. That's a good way of saying it. Well, another domain, if you look at this table. So we'll just think of it as just conversions. We're going to convert to another, from this f of t right here, this big F. We'll look at how we can transform it to get into a form that's more usable. And then we'll transform back and get an equation for t of t is our goal. So what we want is a function t of t. That's what we want. Before we start, let me just define our, probably already seen this, but our deviation variables will become important as we do this derivation. So it's going to be t minus, so t at some time t, minus the initial temperature. And same thing with q, it's going to be q at time t minus our initial q. And we'll notice that for especially that first one, that's 0. So it's really just q at time t. That's a horrible q. We'll move on. You don't care that much. Another thing to note real quick is that because Laplace transforms are linear operations, we can go ahead and chunk this into 3 separate terms. That makes it a little bit easier to write out and a little bit easier to tackle. So our first term, A, is Laplace transform of tau p dt dt. So let's go ahead and look in our table, and we'll look on the left-hand side for something that looks like that. And I think right here, let's go ahead, I like highlighting stuff. That's what we're going to use right there. So we have some constant times that. So let's go ahead and write that out. Our tau p is a constant times s, instead of an f, it's going to be a big T, s, minus that big T at time 0. Now, what we want to remember is that this goes to 0. Our temperature at time 0 minus our temperature at time 0 is equal to 0, which is what the definition of our deviation variable is. And so this just comes to tau p s big T s. Let's move on to B now. B is Laplace transform of, that should be a negative by the way, negative T prime s. That's actually negative T prime T, but it was fortuitous because our Laplace transform is going to negative T s. Let's move on to our third now. It's probably the most challenging, but not bad at all. Kp q prime t minus our dead time. And it's going to Laplace transform with this as well. So the first thing we can do is, again, pull out that constant. And then let's look around for something where we have some form of a step test, or of our QS. What looks like our QS? Well, to me, it's this time delay constant, and this one's going to be one of the more important things. Notice that this big S right here, this big S is a step function. It's not the S of the Laplace domain. That's that S right there. That big S is the step function. And so we have some function that's offset times our step, and a step function of it. It's going to be equal to e to the negative t, and then the offset, so that t is the offset s, times f of s, that function in the Laplace space. So we'll go ahead and we'll multiply by the function in the Laplace space, times e to the negative dead time s. And again, that's the delay. Alright, so let's pull this all together before we do anything else. I'll go ahead and do black so it looks a little bit fancier. We have tau p s t of s is equal to negative t s plus kp qs e to the negative theta s. Let's go ahead, we're just going to draw some dotted lines. Let's go ahead and simplify this. We're going to now work on getting all of our s terms to one side and converting this into something that we can work toward. Again, we're trying to get to this, to that function of t. So we're going to pull all the t's to one side. So we have tau p s ts plus ts is equal to, actually won't even bother writing it, all that. Well, notice that could be written in the form tau ps plus 1 t of s is equal to all that junk again. So t of s is equal to kp over tau ps plus 1 q of s e to the negative theta ps. That's a pretty good form. We're almost there. We have two more things to do. First, we need to figure out what our q of s term is. And then the second thing we'll do is we will look at how we convert this back. So first, qs is equal to what? Well, at time equals 10, q is going to go to 70, and at time equals 0 to 10, it's equal to 0, as well as time equals 70 plus is equal to 0. So we really have two step functions. If we think about it, we have a step up and a step down. Well, where have we used steps? Well, right here. So let's go ahead and think it through. That negative t naught is going to be how far offset it is. So that t naught is going to be where the offset is, and that f of s is going to be our q, but our q is actually a step function. So it's going to be the degree of the step function, so 70 times 1 over s, because that's what the step is. A unit step is 1 over s in the Laplace domain. So let's go ahead, let's do purple for our 70 over s, and it's going to be that for both of them. The degree is the same, so let's go ahead and just do it once. Times, we look over here again, e to the negative 10s minus e to the negative 70s. So let's think this through. It's a step up and a step down. Do little arrows too. But hopefully that makes sense why this right here is negative. It's because it's stepping down, whereas this one's stepping up. So if we put it all together, hopefully this has been at least somewhat, it's going to go right here. So we're going to have T of S is equal to Kp over tau p s plus 1 times 70 over s e to the negative 10s minus e to the negative 70s. We had one last term, which was this e to the negative tau s. So now let's think about how we can apply this to our system, how we can convert back. So let's look up here. Obviously, right off the bat, we know we have some, man, keep on touching this. We know that this right here, man, double man. I will just be very careful. We know that this term right here will be used because we have these step functions. So we're obviously going to have our step function back, and we're going to have some 70 times Kp times 1 minus, or not 1 minus, times a time minus something to get this portion right here. So we're going to offset the time and whatever the time is. The other thing we have, as we look around, I notice we have a tau s plus 1. That looks awfully familiar to what we have in our system. So let's go ahead and let's just think through these two portions just by themselves. We'll switch colors again, just thinking about the puzzle pieces, how we get things in the right terms. So let's think of this as A, and let's think of this as B. A, Kp over 70s tau p s plus 1. So that's going to be Kp times 70 still, times, and what was that quantity? 1 minus e to the negative t over tau. That's actually our tau p, but there we go, that's A. Now B, let's simplify this first. If we have two, we have this exponent and it's going to be distributed to both. When we multiply exponents, it's going to be adding the upper terms, the exponential terms. And we know that our tau from before, let's go ahead and write them out. I'll just move this down just a bit. When we have our initial terms in this problem, we're given what these constants are. So our Kp is equal to 0.9 degrees Celsius per percentage heater. Our tau p is equal to 190 seconds, and our dead time is equal to 15 seconds. Alright, so let's think this through. Our B then is e to the negative 10, and let's go at negative 10s minus 15s, add those together, so it's going to be negative 25s minus e to the negative 15 plus negative 70, that's going to be e to the negative 85s. Wasn't that bad? Alright, now let's look how we're going to do this. We've got some e to the negative stuff over here, right? Right here, let me just erase some of the junk we had before. Right here. So we're going from these portions right here over to this. So the real question is, where does that f of s go? Well, this is the f of s. Is it as simple as that? Could it be? I think so. We're going to have our offsets, and really what it goes down to is there's two things. So this is going to go into two things. Remember, we have these e's, and so we have the function itself, and then we also have, which in this case it'll just be multiplying by the other stuff, but we have the offset. So the function that we're multiplying these by is going to be offset by t minus t naught. That f of s that we're talking about here is the function that we're multiplying by. It's this a portion that's going to be offset. It's the time delay of that a portion. So this right here is our a portion. So that's going to be offset by t naught, by that exponent in our system. And we also have the step function that needs to be added as well. So let's go ahead and let's look at these now. That's going to be, well, actually it's kind of hard to put these two together because we depend on this t is what we need to offset. And is that a negative t or a positive t? Let's think for a second. That's a negative t right here. Keep on coming down. Okay. Just wanted to make sure. So we're going to combine these now. So our t of s, we're almost there. It's t of t now. We're doing good. Is equal to kp times 70 times, and we're going to go ahead and just do this right here first, 1 minus e to the negative, we're going to offset our t minus 25 over tau p. So again, that's in parentheses. And then we have our step function, t minus 25. Then we have this second portion, and because there's that minus sign, we need a minus sign. So minus kp times 70, 1 minus e to the negative t minus 85 over tau p. And again, that's in parentheses just to make it extra clear. Step function, t minus 85. So there we have it. Hopefully that made sense. It takes some time to get used to how to do these Laplace transforms and how to be creative. Like this f of s is our a function, so we can multiply it and just offset the a. Things like that take a little bit of time. Hopefully that makes sense. Let's finish this up and apply this in our temperature control lab and call it a day. Alright folks, we've been doing this activity long enough, so let's get it done. Right here we want to get something that looks like this, where we have our predicted temperatures close to what this actually is. And here's our heater setting right here. So we're going to go ahead, do what we normally do, where we're going to read the temperature control lab data that we already did. The next thing we want to do is take the number of times, take our kp and take our tau p, and I think we want our theta p to be honest too. Oh no, we'll program the theta right here. We have these two step functions right here, and it already does it for you. So it's 0 until 25 and 85, and at that time it is equal to 1. So that does the step function for us. We just have to program the rest. So let's think this through. If we remember right, actually, let me pull it up just to be sure, because I don't want to go through all this and then mess it up now. Let's go ahead and we'll just program it together. T1s is going to be 70 times kp times 1 minus, we're going to go to the exponent. Actually, I forget how to do that in MATLAB. It's been just a bit. Let me Google it real quick. Yep, it's just exp. Should have trusted myself. exp, and that's going to be our time, so it's going to be tm underscore minus the offset. So the first one, we're going to do the minus 25 all over tau p. ta, man, I can't type. And that's close the parentheses for the exponent. So we need one more parentheses up here. time minus 25 divided by tau p. Not too complicated. And then times our S1 for our step function 1. And we'll go minus, and we'll do the same thing. 70 times Kp times 1 minus exp. We'll remember to do 2 this time. And it's going to be Tm underscore minus 85 divided by tau p times our S2. Just a little bit of a small box for us to show all that. In fact, what I'll do, we'll go like this. I'm going to go ahead and copy it, make a comment, and paste it. So hopefully you can see that well. Then we're going to go ahead and plot it. Nice thing is because we're dealing with arrays here, it's going to do all of them for us. That's the nice thing about doing this analytic solution. We can do it in one shot. We'll go ahead, run our section. Invalid expression when calling a function or otherwise indexing a variable. Use parentheses. So when did we index? I don't remember indexing. There was some time where we, it was, I don't know what we did there. Let's look here. There was some time where we didn't have a multiplication thing, is I bet what happened, which assumed that the parentheses would do it. exp, tm. That looks pretty good. Let me copy this. Let's see, maybe I just did something wrong there. So it's Control C, Control V. That was wrong. Control C. I see it right here. Something got put over there. Let's try it again. Oh, so that's our inputs. And do we still get a... You're kidding me. Control C, let's pop it over here so we can debug it together. 70 times Kp times 1 minus exponential time minus 25 divided by, oh, you know it might be? Mismatched delimiters. 1, 2, 1, 2, 3. So this is Kp times 1, 2, 3 open, then 2 closed. So we need a third one closed. Same thing here. 1, 2, 3 open, 1, 2 close. So we need a third one closed. Control C, Control V. Let's try that one out. Thought about that too. S1 is going to be, we're going to multiply that in a, we're multiplying each element. We're doing these element-wise operations rather than matrix operations. So because of that, we're going to want that dot by the operator. So we'll try one more time. One of these times we'll get it right. We can all go home. Invalid use of operator. And we're just going to go like this. I'm going to comment this line out. I'm going to say T1S is equal to, I'm going to go ahead and paste. I believe it should be the dot before the multiplies. See, now we can see the little syntax corrections. And what do you know? We are going in the wrong direction completely. So why would that happen? That's funny, actually. Let me look. So we're going in the wrong direction. Now let's think about this. We're smart. Why would this happen? Because we're graphing the deviation variable. So let's do this instead. To make it the not deviation variable. We would add the ambient temperature, which is 23. So let's start there. I don't think that will do everything. Let's go ahead and run that section. We're still going down and down by a lot when we should be going up in that initial portion. So let's think about this. 70 times Kp times 1 minus time minus 25 times 1 minus the exponential negative. This needs to be a negative right here. Negative. And this one right here needs to be a negative. There we go. And you'll notice our initial temperature was more like 30. We were right on. So let's go ahead and let's make this 30 and let's see how well it matches up. That's not bad. So you can see we have some noise, but we're matching the profile pretty good, especially for something that we can plug in all at once. We're not doing any iteration. This is a straight out, just use Laplace transforms, and we go to the Laplace domain and back. So there you have it, folks. That's our analytic solution. Thanks for coming with me while we all braved the Laplace transforms. Let me know if you have any questions, or let me know if I made another mistake I didn't catch.